Thank you. So, hello everyone. I'm Michał. I prepared this presentation together with Trent, who unfortunately wasn't able to join us today. So I'm here and I'll be presenting this. So let's start from deciphering the title here. About the PyTorch, probably the PyTorch is the part that everyone understands. So this is this deep learning framework that we all use for, and inference is also something that when we have deep learning. So this talk is mostly about deep learning, unfortunately. And inference is the act that we actually use, the deep learning that we trained before. Well, parallel is something that, well, happens in parallel. When two things happen in parallel, they happen at the same time. And the most cryptic part about this title is this Python free threading part. To actually describe this, I would need to first tell what's something that's called GIL, Global Interpreter Lock in Python. So what's the deal with this GIL? We have this snippet of code here. We have this our big fat operation, and let's say this operation is expensive. When you have an expensive operation, one thing to optimize our workload is to run it in parallel. So what we do is like this typical Python code. We just run the operation in threads. Here I used 4 threads, but we can use any number we like, almost any number we like. We just start them, join them, call the parallel processing method. And this, in our expectations, it should pretty and run smoothly across all the 4 threads. Unfortunately, reality is way worse. So in reality, in Python right now, this will look something like this. So this is precisely what GIL is. GIL will block all the threads so that every thread works in isolation from others, and no 2 threads will work at the same time. As you can see, like if I scroll over these two, like at the first glance, we see what kind of slowdowns we are experiencing. So, okay, there might be a question, but parallel processing in Python actually exists right now, right? So what's the reason here? I'm telling that we can't run 2 things in parallel, but in reality, things run in parallel, and we have deep learning frameworks that actually process things quite smoothly. So the thing is that all the parallelism that we have in Python right now needs to be offloaded to lower parts, to the backend, for example. So that's why PyTorch, TensorFlow, JAX, all the deep learning frameworks are actually implemented in C++, because in C++ we don't have this global interpreter lock, and we can use thread parallelism. In Python, we can't use thread parallelism. Of course, there is a possibility to run things in parallel in Python, which I'll cover a little bit later. I would like to show you kind of timeline of the GIL. So GIL was actually introduced in Python 1.0, so it's with us with the beginning of the language. And the interesting part here is that pthreads library, so the library we are all using in C++ for in Unix systems, was introduced as a standard, was introduced in '95. So it's 3 years after the GIL was introduced in Python. And what's more funny even is that first multi-core CPU that was commercialized for commercial use was actually introduced in 2001. So we are dealing with GIL is, let's say, limitation. It not necessarily is a limitation, but it's far from. It was introduced far before we could actually use in our commercial computers use multi-threading features and advancements. And actually, last year, so October last year, October is the month where Python is released every year. And October last year, we released Python 3.13 with the suffix t, and this is the first Python which has the GIL removed. And this is basically what we call free threading. So when the GIL is removed, Python can run. Python runs with threads unlocked and free. The PEP that proposed the removal of the GIL is kind of a special PEP because it has this note at the beginning. This note is special because no other PEP has this note. Basically, what this means is that steering council accepts the PEP, sees the GIL, removing the GIL as an advancement in the language. However, it's not certain that it will come through. It's not certain that that the removing of the GIL is something that we really want. This is because the GIL has its purpose and had its purpose since the beginning. So the fact that we can run things in Python in threads and not be worried about thread safety issues and not to lock, for example, not to lock global variables from things like parallel writing to them, makes single-threaded programs run in more performant way that in the case when we need to care about these kind of issues. Therefore, steering committee is makes it clear that this will be very gradual change. It's specifically they tell that it's not like transferring from Python 2 to Python 3, and there will be no such thing as Python 4 in this particular case. And so the timeline here is spread in time, in many years, and it's in 3 phases. First phase is what we achieved October last year, is creating a build time flag for Python. What does it mean, this build time flag? I'll reach to this in a moment. However, maybe next decade something, or sometime around next decade, maybe, it's not certain yet, the free-threaded Python will be the default. But again, it's not certain yet. Somewhere in the middle, we'll have a runtime flag. So runtime flag is something obvious that when I'm running my Python script like Python -c something or Python something, I can also pass Python -GIL equals 0, for example, and this will run my script without the GIL in unlocked threads. So what precisely is this build time flag? So far, we had one Python version. So Python 3.10, Python 3.11, Python 3.12. The build time flag is a flag that we pass to interpreter when we build Python. So when there's a program in Python, we code it in Python frontend, which is this Python code, and then this is executed by the interpreter. And interpreter is a program written, for example, in C++, so CPython. So CPython is this most common interpreter. There are others like Jython and others. However, I would say that 90% of cases we have CPython. And the build time flag is passed to the CPython when it's being built. And of course, GIL is the member of CPython also. So starting October last year, we have 2 parallel versions of Python. We have Python 3.13, which is the same Python as we had before with the GIL. And we have Python 3.13 with the suffix t. And this is Python without the GIL. And onwards, we'll have the same situation until we reach the point of the runtime flag, which I was mentioning in the previous slide. This creates some challenges. What I put here in this image, this is a typical library ecosystem stack for some deep learning application. So at the bottom we have C++. This is where everything is implemented: PyTorch, TensorFlow, Python, CUDA, right? And going to the top, we have more libraries that are based on our basis of C++, for example. Specifically, things like NumPy, PyTorch, PyBind. PyBind is used to create bindings from C++ to PyTorch, for example, or to other deep learning libraries we are using. They all depend on Python. If we rebuild one of the components of the software stack, like Python in this case, because we are rebuilding the CPython from Python with the GIL to Python without the GIL, we need to also rebuild all the things above this particular component, which is challenging. So imagine the situation that we introduced Python in October last year. Now every component needs to be rebuilt. Some of components will work out of the box, some of them won't. The problem is also with testing, for example. If let's say that I was a creator of a library, and so far I didn't care about any multi-threading issues in Python. Why? In my tests, of course. Why? Because it wasn't possible at all. So when I'm the creator of the library right now, first of all, I need to build this library for free-threaded Python, which might be challenging. And second of all, I need to test it. I need to write some tests. Of course, right now, when we have AI assistant for coding, this is way easier. However, I need to create an environment for testing. This is not a trivial case. And this is, I believe, one of the arguments why the introducing of CPython and this runtime flag and default free-threaded Python will be spread throughout time, because it needs serious work put in the environment to actually do it, to ensure everything is working. So going back to the to our timeline, I believe that something that most developers, all of us here in this room, cares is actually not some random Python version. I'm using Python 13 since October last year, but I don't think that everyone will do so. Especially the many tools that we have, PyTorch, for example, support mostly the Python version that's included in Ubuntu LTS version, right? So if we map our Ubuntu LTS version to this timeline, we have Ubuntu 26 LTS, which will appear next year in April, and Ubuntu 28. Most probably, the runtime flag will happen somewhere in between. So we could expect that somewhere between 2026, 2027, this will be the moment when we can run Python with the flag, not the separate version of a free-threaded Python. Why? Because probably we would like to have this version in the Ubuntu 28 LTS, because this is major step. And about the default free-threading behavior, we don't know. When we have the runtime flag, the community will start a discussion. Do we want this to be actually the default behavior or not? I also put here some levels of support. This is something that when I was working on the adjusting NVIDIA software stack to free-threaded Python, I figured out that there are some kind of levels of support. So the level 3, this is the level that library does not work with free-threaded Python. It can be built even. The quite simple step is go from level 3 to level 2. Let's build a library for free-threaded Python. This wasn't the case always. This is a problem with all the dependencies we use for building. However, it can be achieved right now quite easily, because many dependencies, especially binding technologies are already adjusted to free-threaded Python. Then going from step 2 to step 1 is also rather easy. And I would say it's even free in this case, that there will be only scarcely situation when if my library run and if I build it for free-threaded Python, it won't run for in a single-threaded manner. Single-threaded behavior will be achieved quite easily. But now going from level 1 to level 0 is the most problematic part, because running something in multi-threaded environment, I would say also implies running tests and testing my solution, and this is obviously not easy. So I would like to show you two cases of using free-threaded Python in Inference with PyTorch. First of all is parallelization of data processing, and second of all is LLM inference with HTTP server. So let's start from data processing, pre-processing parallelization. So this is a situation, this is a scenario that doesn't happen often right now, but let's say that we have a convolution neural network, some kind of network for classification. The typical situation here is that my convolution network is first of all accepts only static size, right? So my image needs to be resized and most probably also normalized for this network. However, there's also a situation that when I load my image to the CPU, it needs to be decoded. This is actually quite expensive operation, and we do have tools to decode images on the GPU. This is quite important thing especially in training, but in inference also. So my typical workload or pipeline looks like I'm loading the image of llama into CPU. CPU decodes it, resizes, normalizes. Then it sends to the neural network my convnet, and the convnet tells me that, okay, it's llama. So the bottleneck in this image is the CPU part, because it's really, really slow. So first thing that comes to my mind, what can I do with this, is actually I can parallelize this. Let's say that I load 3 images, my batch is 3. Every such image can be in parallel processed, right? So decoded, resized, and normalized. However, let's say that I want to do this inside threads. What do I say? There's a GIL, right? So GIL prevents this. Actually, there is a way how we can parallelize such processing. This can be done in 2 ways. First of all, I can use not threads but processes for parallelization. This is something that Torch data loader, which I will talk in a moment about, Torch data loader actually allows. But I can also do it in C++. That's something that we want to do, right? So we want to write code in C++ if we want to do something in Python. So the Torch data loader. Torch data loader allows us to parallelize processing within processes, not threads, right? It works. That's great. So what Torch data loader does is it fires a process for my particular image processing operation. It creates one process, and parts of my batch will go to process, for example, depending on configuration. However, next step, as I was telling earlier, next step is to have the decoding not on the CPU, but on the GPU. This is certainly faster operation. Also resizing, right? Normalization. So the things that for example, Jacob was telling yesterday on tutorial, the operations that work on tiles. These are operations we want to use on GPU. We want to run on GPU. So let's say we do have this processing on a GPU, and we do it something like this. So we run one process per operation on the GPU. Well, this actually is a bad practice. Bad practice assuming you have one GPU. So yeah, I would like to emphasize that this is, if we have one GPU, we don't parallelize, we don't run GPU operations within processes. The reason here is that something that's called CUDA context switching. So when we have processes, every process needs to have its own CUDA context. Like we can't share memory between processes, right? There are tools for sharing memory between processes like IPC. So every process needs to have its own CUDA context. Let's say we have image decoding here only. Image decoding happens on the GPU, so there's a CUDA context involved. And if one process decodes image on a GPU using one CUDA context, and then the second process wants to do this also, the CUDA context, GPU needs to switch the context. And this is a very expensive operation. However, if I would use threads for it, I can share the CUDA context. So there's only one. And now every image decode in decode function can use this one particular CUDA context, and it doesn't need to be switched. This is quite good speed up here. And how much is the speed up? Well, we ran the numbers, we ran the benchmark, and this is quite significant, right? So this benchmark is something that I showed in a minute before. So this is only the image decoding operation, which was parallelized in two manners. First is processes, and the other is threads. As we see the numbers, processes saturate after basically second worker here. However, when I use threads, the speed up just grows with the number of workers. So again, the reason for this is that CUDA context switching is a very expensive operation. We shouldn't use GPU operations parallelized in processes. There should be, assuming, of course, we have one GPU. There's, of course, when you have multiple GPUs, the typical approach is to have one process run on one GPU, the other process run on the other GPU, and everything works as it should. In this benchmark, we also measured memory consumption. This is a CPU memory consumption. And so not surprisingly here, when we use processes, not only we have multiple CUDA contexts, but every process is forked from the parent process and takes, this is a CPU memory consumption, and takes some memory, right? When we have threads, we don't have this issue, right? So threads have, there's only one process involved. So that was the first case. The second one is PyTorch inference using parallel HTTP server. So this was actually an LLM. Let me remind you how LLMs work. So when I have LLM on the right side of the screen, and I have a prompt, the prompt goes in the input of the LLM. The LLM creates a token, which is appended to my prompt, and my prompt is and my LLM is fed yet another time with the prompt. And this process is iterative process, runs in a loop unless one of two things happen. First of all is end of sequence token, or the max length is reached. So and at this point everything goes back to the user. So let's say that I would like to create a ChatGPT like service, right? So I have LLM, my user, this is a typical case. I have LLM, my user writes a prompt. So what I need to do is to create HTTP server. HTTP server will get my prompt, it will feed the LLM, and this process will happen. But actually this is wrong. When we create ChatGPT, when you use ChatGPT, we see that tokens appear token by token. And this process, and in this kind of situation, our whole response will appear at the end of the process. So we need to modify this a little bit. What we need to do is to create a communication between user and HTTP server after every token. So this creates yet more load on the HTTP server. And now let's imagine that on the left side of the image we have many users. The HTTP server is loaded with communication. Assuming that we want to, of course, there are tools for this, and this is a solved problem in other languages than Python. but assuming we would like to run this HTTP server purely in Python. So typically what I would do is I would handle every request in a separate thread. So my HTTP server will have some kind of thread pool. There will be queue of requests. When thread is finished with previous request, it takes another request from the queue and processes it. And what we have here, of course, the threads can't run in a parallel manner. They run one by one. So we have the GIL again. What we could do then here is to build this HTTP server in a 3-threaded Python. So something like this. In this situation, threads run in parallel, and everything should run smoothly. And the fact is that it did. We also run the numbers. So I actually run it in two setups. First one is I used 32 threads for HTTP server, and the second one is I used 8 threads. These numbers, we see that average latency is quite high in the situation with GIL, and quite low without the GIL. But the real interesting number here, and the number I should explain here, is the throughput. So the chart in the far right. As we see, the throughput when we have 32 threads, the throughput in the HTTP server is extremely low. It's almost zero. It's almost this benchmark ran in, I believe, 120 seconds, so 2 minutes, and almost no request passed. Right. So this is actually because what I have here is the CPU utilization of the server with the GIL. So whenever requests were processed in a parallel manner, however, they were so the switching between threads and the GIL was hogging the whole system so much that first of all, CPU was totally underutilized. And the throughput was extremely low, almost no request passed. And this chart is a latency distribution of this particular case. So we see here that I believe it's like four samples four requests that passed, while in a GIL case, in a no-GIL case, sorry, it was like very the latency was very low and spread across almost the whole spectrum. There is a peak on the 100%. So this particular peak of latency is caused by the situation that no-GIL Python is still a little bit slower than GIL Python in a single-threaded manner. So this particular sample or 2 samples that were at the end of the processing were the samples that they run not in parallel because it wasn't yet a parallel distribution, and only, for example, 1 or 2 samples came to the server. So this is something that we could actually expect, that single-threaded processing in a GIL with the GIL is slower than is faster, sorry, than the processing without the GIL. However, the benefit here is that we use multi-threading, so we use threads to parallelize things. I run this also with 8 threads to show that actually this server with the GIL works. So this was the situation that the system, the program wasn't hogged with the GIL. There was no so much request that would provide such problems. And we do see, if we compare these to the previous one, we do see that the throughput of the GIL case is higher, and the throughput of the no-GIL case in a situation with 8 threads is also higher. Oh my god. Yeah, but so this is probably still a situation that I didn't run the utilization here. So I can't answer precisely the question why is it like this, but I believe that I don't remember also how many threads were in my system. However, this might be the case that more threads were actually creating a higher load on the server. And this is the latency distribution here. So something that we see is like we see two things basically. First of all, is that the GIL case is actually better. Like we have more data on the GIL case because the system wasn't hogged, and we do see on the right side no-GIL case is also better in most of the cases. And on the right side, we see those weird steps. So this is the situation where most probably the requests were there was contention on some resources. For example, the PyTorch that we see here, PyTorch build here, is pre-threaded. The PyTorch build here is on level 1 of my support, so it does run in a single-threaded manner, but it doesn't run on a multi-threaded fashion. So the log here in this system was on a PyTorch, for example. PyTorch needed to run inference in sequential manner. And this is basically all I prepared for today. So I will share this presentation, obviously, and a couple of things that you can look at to learn about free-threaded Python are the links here. First of all, DPO. There's also a Discord server about free-threaded Python. I linked here 2 articles. One about the PyTorch inference scenario I talked a little bit a minute ago, and the blog post about parallel data processing before. And lastly, at the PyCon, which happened like a few weeks ago, there were some interesting presentations. I believe those presentations are, I don't know, yesterday or 2 days ago were published. So I linked here slides, but you can find those presentations on YouTube. Yeah. So that's all from my side. Are there any questions?